Steam engines transformed the world before anyone understood why. Sadi Carnot, a young French engineer, posed a revolutionary question: how efficient can heat engines be? His 1824 Carnot cycle defined the theoretical maximum efficiency and founded modern thermodynamics. Carnot discovers a profound truth: no engine can convert all heat into work. Maximum efficiency depends solely on temperature differences between hot and cold reservoirs, never on design or materials. This thermodynamic limit reveals perfect efficiency remains physically impossible, a law of nature itself. In his family's Manchester brewery, James Prescott Joule conducts an elegant experiment. A falling weight drives a paddle wheel through water, raising its temperature. His precise measurements reveal heat and mechanical energy are interconvertible. Energy itself remains eternally conserved. The British Association dismisses Joule's findings with polite indifference. Yet William Thomson, attending that fateful session, grasps the profound significance. He becomes Joule's champion, recognizing that scientific truth requires both brilliant minds and attentive witnesses to propagate. Rudolf Clausius formalized the second law of thermodynamics in 1850, revealing heat's inexorable direction, from hot to cold. Work converts entirely to heat, yet heat cannot fully become work. The universe marches toward disorder. Clausius named this irreversibility entropy in 1865. The second law of thermodynamics reveals entropy's relentless march. In isolated systems, disorder inevitably increases. Energy disperses, heat dissipates, order crumbles into chaos. This irreversible process defines time's arrow, explaining why eggs shatter but never reassemble themselves spontaneously. Ludwig Boltzmann reveals thermodynamics' hidden truth: temperature measures the average kinetic energy of countless atoms in motion, while entropy counts the microscopic states underlying each macroscopic condition. Thermodynamics emerges as statistical mechanics made visible. Boltzmann's equation etched upon his Viennese tomb defines entropy as the logarithm of microscopic arrangements. His statistical interpretation vindicated atomic theory, yet brought fierce opposition. He took his own life in 1906, 1 year before atoms were finally confirmed. William Thomson, Lord Kelvin, transformed Carnot's theory into absolute temperature in 1848. Absolute zero, minus 273.15 degrees Celsius, marks where molecular motion ceases. The Kelvin scale begins there, a theoretical limit forever beyond reach. Heat pumps reverse nature's flow, moving warmth against its gradient through mechanical work. Vapor compression refrigeration, perfected in the 1850s, applied this thermodynamic principle to transform food preservation and global trade forever. The steam engine preceded its theory. Carnot, Joule, and Clausius explained why it worked and defined its efficiency limits. This knowledge guided future engineers, revealing how much improvement remained possible. Theory and technology engaged in dialogue, making the Industrial Revolution comprehensible. Power stations worldwide operate on Sadi Carnot's 1824 principle, extracting work from temperature differences. Whether burning coal, gas, or splitting atoms, they all reject waste heat to cooler reservoirs. The global electrical grid runs on 19th-century thermodynamics. From Carnot's efficiency limits through Joule's heat measurements to Clausius naming entropy and Boltzmann linking atoms to thermodynamics, the steam age transforms understanding into power. Energy becomes physics itself, and physics becomes civilization. I am Takku. The steam engine transformed civilization before thermodynamics could explain why it worked at all. Subscribe to Wisdom of Takku, because understanding always follows the courage to experiment.